Orbital mechanics. Like a lot of physics, orbital mechanics can get very complicated very quickly. However, in IB physics, you do get introduced to some really fundamental ideas about orbital motion, as well as some maths to go along with it. The IB physics syllabus asks you to be able to derive and understand the formula for orbital speed, and find the total energy involved in an orbit. However, they often also test your knowledge of Kepler's third law, admittedly a little bit indirectly, so we'll go over deriving that as well. First, I want to point out some of the assumptions that we're making in our systems. Technically, in orbits, both bodies orbit around a common center of mass. This issue really only has to be considered when the two bodies are of similar mass, and so their common center of mass is far outside the center of one of the bodies. For example, in some binary star system, the two stars are similarly massed, and so they orbit around a point in between them. So we're going to work with systems where one mass is much larger than the other, such that the center of mass of the system is approximately at the center of the larger body. With that in mind, let's consider the orbit of one of the satellites orbiting the Earth. Assuming the orbit is circular and has a constant orbital linear velocity, using our equation for centripetal force, we know that the force pulling on the satellite is equal to its mass, which we're calling lowercase m, times its velocity squared over the radius of its orbit. Furthermore, since the centripetal force can be attributed to the gravitational force, we know that the force on the satellite is also equivalent to the expression for Newton's law of universal gravitation. The gravitational constant multiplied by the mass of the Earth and the mass of the satellite divided by the square of the radius of the orbit. So we can equate these expressions and find the velocity of orbit with some simple manipulation. The mass of the satellite cancels on both sides and r. Then we're left with velocity squared equaling g times big M over r, which is an equation you should actually tuck away to be used a little bit later. So velocity is the square root of big G, big M over r. That's our first equation out of the way. Now this next bit is a little bit out of the syllabus, but there have been plenty of exam questions on it, asking students to derive this relationship. What relationship? Well, what's the relationship between the period of the orbit, the time somebody takes to complete one orbit, and the radius of its orbit, which is Kepler's third law? There is very clearly a relationship there, but where would we begin? Well, since we've assumed the velocity is constant, as a rule of uniform circular motion, we know that the velocity is equal to the average velocity, and is therefore equal to the total distance traveled in an orbit over the total time taken to complete an orbit. The total distance is just the circumference of the circle, which we know is 2 pi r, and the total time is just the period of the orbit. As we've already seen, the velocity in an orbit is equal to the square root of big G big M over r. But if we got rid of that square root, we'd have an expression for v squared. Now, if we substitute this other expression that we have for v that includes the period, then we're almost finished. We just distribute that squaring function across the expression, and then rearrange the equation to have t on one side and r on the other. So we end up with the equation t squared equals 4 pi squared over big G big M multiplied by r cubed. So there you go. The period squared is directly proportional to the radius of the orbit cubed. That's Kepler's third law, that proportionality right there. Alright, now the final thing we're covering in this video is introducing energy into orbital mechanics. The total energy of this system will be its kinetic energy plus its gravitational potential energy. I think that's pretty clear. Its kinetic energy is very easy to calculate, as we're assuming the larger mass isn't moving, so all you're doing is 1/2 mv squared for that smaller mass. However, the GPE is slightly more complicated. I've made a video with a more rigorous proof using some calculus for the equation for GPE, which I've put into the info bar for you to click on now. But for now, just know that it's equal to negative big G big M little m over r. That's the expression for gravitational potential energy. So our equation now looks like total energy equaling 1/2 mv squared minus big G big M little m over r. This is correct, but can actually be greatly simplified. First, remember that v squared equals big G big M over r, as we've shown when finding orbital speed, So we can substitute that back into our expression for kinetic energy, and then put everything on a common denominator. Look at that. That's just 1/2 the expression for GPE. And perhaps even more simply, it's just the negative of our kinetic energy. And so the total energy of some object in orbit is the negative of its total kinetic energy. That's just about everything you need to know about orbital mechanics. I have another video where I derive the formula for gravitational potential energy using calculus, if you're interested, and I have put up another video that might interest you on the screen now. Thank you for watching. Bye-bye.